Hello everyone and welcome to Merkland 360. So in this video I will solve a question with you to illustrate um deformation and axial loadings. All right. So now we have a compressive centric forces of 40 kips, which is kilopound, are applied at both ends of the assembly shown by means of rigid end plate. Now, knowing that ES, so ES is like the shell, and then EA, so the shell is aluminum, so ES is for the, ES is steel, and then EA is aluminum. So we have aluminum shell and then we have steel core. So these are the values. So the S here represents the steel, and then the A represents the aluminum. All right. Now the question is saying that we should determine the normal stresses in the core, so the steel core and the aluminum shell, and then the deformation of the assembly. All right. So when we say compressive centric forces, it means that the load is actually sort of passing through the center. All right. So something like this. Now we have a core and then we have a shell. So some portion of the load will be taken by the steel core, and then some portion of the load will be taken by the aluminum shell. So let's solve it together. Now so we have to say something. Let PA represent the portion of the load carried by the aluminum, and then PS, okay, let me write it. PA is equal to load on aluminum, and then PS will be the load on the steel. Now, having done this, we can say that in terms of deformation, what do we know? So we know that deformation is PLAE. All right. Solving for P. So in terms of, okay, let me do it this way. Deflection will be in terms of aluminum, and then PL over AE for steel. Now we can say that in terms of aluminum, the load can be expressed as delta, okay, AE delta divided by L, and all of this is for the aluminum. Again, for the steel, we are going to get the same thing, but this is for aluminum and then this is for steel. All right. Now from here, what do we know? So the total force or the total load P will be carried by A and then S. So in other words, the total load, some will be carried by the steel and some will be carried by the aluminum core. All right. Now we can say that the total force can also be expressed in terms of okay. So this is what we are saying. Let's try to add this divided by this plus this divided by this. Now, interestingly, you can see that the entire length will be the same because this and this will have the same length. So it's like some sort of aluminum steel, and then there is a shell of aluminum steel core, and aluminum shell. So they will have the same length. So you can factorize out the length, and then they will actually have the same deflection, because that is the deflection that we will be looking for. So we can actually factorize and say that our so we are going to actually get something like this: delta over L, then we have area of aluminum, and then we have Young's modulus of aluminum plus area of steel, Young's modulus of steel. So this is the expression for the load. Okay, now from here, what do we know? So we know that delta over L is what? Okay, so we know that strain is delta over L. That is the formula for strain. That is elongation over the actual length. So we can actually bring it here so that we have AAEA plus ASES. All right. Then what can we say? So the total strain, is going to be okay. Let me do it this way. I want to take my time and do it so that you understand what we are doing. So the total strain will be given by making the strain the subject. It will be P divided by AAEA plus ASES. So epsilon, which is the total strain, will be so we know okay, let's calculate the areas. First of all, let's calculate the areas before we apply the formula. So the area of aluminum, let's go back. So the outside is aluminum, therefore the diameter is what? The 2.5, because that is the one which is outside. Okay, so the area of the aluminum will be what? Okay, so the area of the aluminum will be pi over 4 d out squared minus d in squared. Why? Because if we have an outer diameter, then we can say that this outer and this inner. So if we want the aluminum diameter or the area occupied by the aluminum shell, it is actually this area, which is the outer minus the inner. Now the outer is 2.5 and the inner is 1, just 1. So it will be pi over 4 2.5 squared minus 1 squared. And if we do this, we will get the area for the aluminum. Let's pick our calculators and compute this area. So it's going to be, so pi divided by 4 multiplied by so 2.5 squared minus 1.0 squared. So 4.12 squared inch. 4.12 squared inch. And then, or maybe let's take the area to 4 decimal place. So 4.1233. Okay. Inch squared. Similarly, for the steel, so the steel is this one, the one which is inside, is the one which is inside. So the steel is only here. So for that one, we are going to use only the diameter, which is 1. So it's going to be pi, d is 1. So it's just pi over 4. So what is that going to be? We can pick our calculators and do this. So pi divided by 4. So 0.7854. 0.7854 inch squared. All right, so we have AA and we have AS, and we also know the Young's modulus. So the total strain using this formula we have developed here, the total strain will be what? The load, which was given as 40 KIPS, this one, 40 KIPS, and then divided by the area, which is 4.1233. Then we multiply by the Young's modulus of aluminum, which is 10.1 times 10 to the power 6. So 10.1 times 10 to the power 6. Then we add it to the area of the steel core, which is 0.7854. And then we sort of multiply this with the Young's modulus of steel, that is 29 times 10 to the power 6. So 29 times 10 to the power 6. So 40 times 10 to the power 3. Now this strain, so what will be the formula? What will be the strain? Let's calculate it. So 40 times 10 to the power 3, 4.1233 multiply by 10.1. Okay. So multiply by 10.1 times 10 to the power 6 plus 0.7854 multiply by 29 times 10 to the power 6. From here, okay, so what this means is that the strain is given by 6.209 and then multiply by 10 minus 4. This one is having no unit, so that is the answer. But what do we know? We know that sigma is E epsilon, right? So if I know the total strain, then the fraction of the stress which is carried by the aluminum or the steel, we can calculate it, right? So we have okay, so for the steel, we will have E of the steel multiplied by the elongation, the strain, and E of steel is 29 times 10, 29 times 10 to the power 6. Then we multiply it by the strain, which is 6.209 times 10 minus 4. But there was supposed to be a negative sign. Why? Because this load will cause some sort of how do I put it? It's going to cause some compressive stress on the structure. It's going to cause a compressive stress on the structure because of the load. So then it's supposed to be minus, actually. And then also I think there was a mistake here. P, when I was calculating P, Oh, okay. All right. So all right. All right. So this is what we have. Um so it's going to be 29 times 10 to the power 6 multiplied by 6.209 times 10 to the power minus 4. So we have 18,006. 18,006.1. So in other words, 18.0 KSI. So that is the normal stress carried by the steel. Now, if we want for the aluminium, it's going to be EA epsilon, which is what? 10.1 times 10. In fact, this one was supposed to be minus, so because of the compressive stress, 10 to the power 6 multiplied by 6.209 times 10 minus 4. And what is that? So I will just change the Young's modulus here and make it 10.1. And that is 6,271. 6271.09. So approximately sigma A will be minus 6 point, so minus 6.27 KSI. All right, so this is it for the stress, the normal stress in the aluminium. Okay, now the last part of the question says we should calculate the deformation of the assembly. So now the deformation delta is the same as the strain over the, oh no, the strain is the change in length or the elongation divided by L. Now deformation will be strain multiplied by length, but we know the strain, which is what? So minus 6.203 minus 6.209 times 10 to the power minus 4. Minus 6.209 times 10 to the power minus 4, all multiplied by the length, which is 10, because the length was 10 inch. Okay, so what do we get for the elongation? So minus, okay, let's multiply it. Minus 6.209 times 10 to the power minus 4 multiplied by 10. Okay, so minus 6.209 10 to the power minus 3 inch, and that is our deflection. All right, so this problem has been solved. Thank you very much for watching.